Hey, this is Horner. We're going to look at the second part of the problems from Chapter 8. These deal with the biological applications of torque and angular momentum. In the very first question, we've got the movie Terminator. We have Arnold Schwarzenegger lifting somebody up by the neck, and with both arms fully extended, he's holding that person off the ground. The person weighs 700 newtons, and we know from the shoulder joint here all the way out to the very end where the person's being held is a distance of 60 centimeters. Because the person is 700 newtons, one of the things that we need to do, and they're being held by both arms, we want to know what is the force in each of the deltoid muscles, which means we have to take this and we need to divide it by 2. So the force of the person, which is actually going to be right here pointing down, so that's the force of the person, should be equal to 1/2 of that 700 value. So the force of the person on each one is about 350 newtons. Let's talk about the rotational components of what's going on here. So the deltoid muscle is attached to the bone right here, and we know that it will lift that bone up and to the left, similar to that. Since that is counterclockwise, we're going to call that a positive torque. If this person was to let go or just relax their arm, we know that at the center of gravity it would rotate this way, so that would be a negative torque. And then same thing with the end of the hand, we would go this way, and that would also be a negative torque. The sum of the torques here should be equal to 0. And let's go ahead and look at each one of the torques as we go through. We have the force of the muscle, so Fm is the force of the muscle, and notice that it's at a 15-degree angle, and because of that we're going to do the radius for that muscle, but then we also need to add in the sine of 15 degrees since there's an angle that that force is acting at. Now we're going to go ahead and do the next one. That would be for the arm itself. And so that would be the force of gravity on the arm. And we also need to multiply that times the radius that the force of gravity on the center of gravity is acting on. The last thing is that force of the person, and so this is minus the force of the person times the radius of where that person would be from the point of rotation, and those should all be equal to 0. Let's go ahead and put in our radius for each one. So Fm times the first radius, which is 12, times the sine of 15, minus Fg times the radius to the center of gravity, which is 27.5. And then we're going to subtract off of that the force of the person that is being held up, and we'll multiply that times the last radius, which is 60 centimeters. And those are all equal to 0. Let's go ahead and put in our forces now and resolve some of these other things. So the force of the muscle times 3.11, so that's the product of 12 times sine of 15, minus, and then the force of the arm. Now this 30 comes from the figure, and that's in the book. So remember, these are all out of your book, and this is 30 newtons altogether, because it's 3 kilograms. So we're going to multiply that by 27.5, and then we need to subtract off of 1/2 of that 700 value times 60. You could also have just put in the 350 that we did earlier, and those are all equal to 0. At this point we know that Fm is equal to Fm times 3.11, so I need to get rid of these things. 3.11 is equal to 21825. So I just went ahead and did the products of these and then added the 2 together. Notice this is negative and this is negative, so you're going to add the 2. And then when you go on the other side, it'll get rid of the negative. So now we know that the force that the muscle has to exert is 7,018 newtons, and that is a tremendous amount of force for that muscle to be doing. But it's Arnold Schwarzenegger. Let's go ahead and take a look at number 46. It's the next one. In this one, you are holding up a carton of milk, and they want to know, with your forearm parallel, your hand is 35 centimeters, so you can see that here, from the elbow to the milk. They also tell us that we have a distance here of 30 centimeters. The weight of the forearm and the empty hand is 18 newtons. So I know that there's my 18 newtons just for the forearm weight. The milk carton weight is 9.9 newtons, and the center of gravity is at 16.5 centimeters. We're going to do the sum of the torques again. So the sum of the torques here should be equal to 0. We know we have several things rotating here. So the force of the bicep is pulling up, and we know it's pulling up in this direction. We know that the center of gravity, in fact, I'm going to move that so it's not real confusing here. I'm going to move it over to where it's actually touching. So that is the rotation. If the arm was to relax, you know it would fall this way. So that would be a negative. This would be positive. And then the milk pushes down on the hand, so that force would be in this direction, causing a torque around the elbow joint there, and it would also be negative. All right, so let's start off with looking at the furthest thing out, which is the force of the milk. So this is going to be negative, the force of the milk, times the radius of the milk, where the milk is at, minus the force of gravity. And we're going to use Fg because that's the center of gravity. That will help us just be consistent as we go through. We're going to take that times the radius for the center of gravity, plus the force of the bicep times the distance from the bicep to that pivot point. Those are all equal to 0. Force of the milk we know is 9.9 newtons. Radius of the milk is 35 centimeters. We're going to leave it that way because remember in this one we're going to solve for FB. Now we're going to subtract off 18 times 16.5. Oops, 16.5. Ooh, that's really ugly. So let's subtract off 16.5. So here's 16.5. And then we're going to add to that FB times the radius of the bicep. I put G there, and this really should be B. And the radius of the bicep is 5, and that's equal to 0. So now if you do your math and you're going to move these to the other side, we're going to have the force of the bicep times 5 is equal to 643.5. And so the force of the bicep is going to be 128.7 newtons. Moving on to the next problem. Let's move on down here. Now I have a person doing leg lifts, and they've attached a 3-kilogram ankle weight down here on the bottom. It says the quadricep muscles are attached to the patella via a tendon. So here's the quadricep muscle, here's your patella, and then there's that tendon in between. And it says attaches to the bone about 10 centimeters below the knee joint. So then we've got this, you'll see the patella, we've got the tendon that actually comes up and over and then connects to the tibia itself. The lower leg has a mass of 5 kilograms and its center of gravity is right here. It's about 22 centimeters below the knee. The ankle weight is 41 centimeters from the knee, and they want to know if the person lifts one leg, find the force exerted by that patellar tendon to hold the leg at an angle first of 30 degrees and then finally at an angle of 90 degrees. So we're going to do the 30 degrees first, and then it's very easy to solve for the value for the 90 degrees. That won't be too bad. We'll start over here, and this is letter A, and we're looking at this at a 30-degree bend. So we're looking at it at a 30-degree bend. So by 30 degrees, they're measuring from the vertical. So this right here would be 30 degrees. When you do the 90 degrees, you know that's going to be where the leg is fully extended and it is horizontal. Sum of the torques. So the sum of the torques here should be equal to 0. And so we've got several things here that we have to worry about. We know that this patellar tendon is rotating the leg in this direction. So we're going to say since that's counterclockwise, that is a positive torque. We also have the center of gravity is going in this direction, so there's a negative torque, and then finally from our leg weight is going in this direction, and it also is a negative torque. Let's start with the patellar tendon force, so that's FP. We know the distance is our radius here is going to be RP, and then notice that we also have an angle that patellar tendon is working on the tibia at. And so that is 30 degrees. Yeah, that one is 20 degrees right there. So what we need to do is we're going to say that's times the sine of 20 degrees. We're going to subtract off the other now, so we have the force of gravity at the center of gravity times the radius, and we're going to take that times the sine of 30 degrees, since now this is the angle that we're working at for the leg coming up. So notice the patellar tendon is working at a 20-degree angle, but the leg and the weight are working at a 30-degree angle. So now we're going to take and just say the force of the weight times the radius of the weight times the sine of 30 degrees, and all that should be equal to 0, and it is. We want to find the force of the patellar tendon, so the force on the patellar tendon is going to be equal to the force of gravity times the radius where that center of gravity is times the sine of 30 degrees plus the force of the weight, radius of the weight, times the sine of 30 degrees. And we're going to divide all of that by the radius of the patellar tendon to the point of rotation, which is right here, and that's times the sine of 20. So we just took what was right here once we moved everything to the right side, and we divided both sides by RP sine of 20. If you plug all your numbers in, here you're going to have 50 times 22. Then you're going to multiply that times the sine of 30. You're going to add to it 30 times 41 times the sine of 30. And we're going to divide by 10 times the sine of 20. So that fills in all the numbers that we were given. You end up with about 550 plus 615. And we're going to divide that by 3.42. So you end up with 341 newtons. When we do the sine of 90, remember the sine of 90 will give us a number equal to 1. So I can just redo this equation again, but because I don't have a sine of 30, that makes this problem a lot easier. So now the force of the patellar tendon is equal to 50 times 20, so that's the same thing that we had before. Actually, it's 50 times 22. 50 times 22 plus 30 times 41. And we got rid of the sine of 90 because it's 1. And then we're going to divide by 10 times the sine of 20, since that's what we had on the bottom here. And when you're done, you end up with 652 newtons. And that makes sense. It should take a lot more force in order to hold the leg straight out than it does when it's just bent at about a 30-degree angle. So you've got 60 more degrees of rotation. And with that 60 more degrees of rotation, you little less than double the force that you need to pull that leg up. And that is number 47. That's one of the harder ones to do, I think. Number 77, this one's a lot easier. It says a figure skater is spinning at a rate of 1 revolution per second with her arms outstretched. She then draws her arms into her chest, reduces her rotational inertia by 67%. She spins a lot faster. They want to know what is her new rate of rotation. So we started at 1, so we know that the new rate should be higher. The new rate should be higher. To do this, we're going to use the conservation of angular momentum. It's just like the conservation of momentum, where we said that the original momentum should be equal to the final momentum. But now we're doing everything in a circle. So we're going to say the original angular momentum should be equal to the final angular momentum. Remember, angular momentum is equal to I. So this is the original times the original speed, angular speed. And that's equal to the final angular, moment of inertia times the angular speed. We want to find out what is WF, and so that's equal to IO over IF, and that's times WO. Now, we also need to recognize it says that the ratio between the two rotational inertias here, IF over IO, is equal to 0.67. So if IF over IO is 0.67, IO over IF is going to be the inverse of that. So I just do 1 over 0.67. We're going to take that times our original value for the rotational speed or rotational velocity. And when you do this math, you should end up with 1.5 revolutions per second. And so yes, it is bigger than the original 1.0 revolutions per second. Let's go ahead and take a look at the next one. This is number 78. We have a skater initially spinning at a rate of 10 radians per second. with a rotational inertia of somewhere around 2.5 kilograms times a meter squared when the arms are extended. What is her angular velocity? She pulls her arms in and reduces her rotational inertia to 1.6. So very similar to the last one that we did. Here we're going to say the original angular momentum is equal to the final angular momentum. So we can go ahead and put in what the formula is in for each one. So LO is equal to IO times omega O. That's equal to IF times the angular velocity. And that would be final, not original. So our final angular velocity should be equal to IO over IF. This time they didn't give us a ratio. We actually have to just use the numbers. So our IO here is 2.5. That was our original rotational inertia. Final rotational inertia is only 1.6. And we're going to multiply that times the original velocity, angular velocity, and we end up with 15.6 radians per second. So same problem as we just did, actually, except for instead of a ratio, they actually gave us our numbers. The next one looks like it is the same thing, but this one actually says how much work. This one is asking for what is her angular velocity. So big difference between the two. Remember, work is equal to the change in energy, and here it's going to be the change in kinetic energy. And I know that the kinetic energy for something that's rotating is equal to 1/2 times I omega squared. So just like 1/2 mv squared, but I is for rotational inertia, and instead of v squared I have my rotational velocity squared. Let's go ahead and plug everything in. So the change in kinetic energy is going to be, rotational kinetic energy is 1/2 of IF omega F squared minus 1/2 of the original rotational inertia times omega O squared. Go ahead and put our numbers in. This would be 1/2 of 1.6 times 15.6 squared, and we got that from up here. And then that's minus 1/2 of 2.5 times 10 squared. And so when you do your math, you should end up with somewhere around 70 joules. For number 82, which is the next problem, we have a diver can change his rotational inertia by drawing his arms and legs closer to his body. When he leaves the diving board with some unknown angular velocity, pulls himself into a ball as closely as possible and makes 2 complete rotations in 1.33 seconds. So 2 rotations, 1.33 seconds, there's a rate that we're going to need to use. If his rotational inertia decreases by a factor of 3 when he goes from the straight to the tuck position, what was his angular velocity when he left the diving board? So we're looking for what is the original angular velocity. We know that the angular momentum is conserved, so LO is equal to LF. So that's IO omega O is equal to IF omega F. We're going to look for omega O, and that's equal to IF over IO times omega F. They said that his rotational inertia decreases by a factor of 3. So that means that this is going to be 1 over 3 times my omega F, which is going to be something we need to figure out. So here we've got 2 revolutions, and that's happening in 1.33 seconds. So we said that's a rate, but we need to get this in radians per second. So this is 2 pi radians for every 1 revolution. We already have seconds on the bottom, so we don't have to do anything with it. And you end up with 9.45 radians per second. 1/3 of 9.45 then, and we end up with 3.15 radians per second. Let's go ahead and take a look at the next one. This one is number 83, so we only have a couple more here. Number 83 says you've got the rotational inertia of a diver in a pike position is 15.5 meters kilogram meter squared, and it's only 8 in a tuck position, and they show you what each one of these looks like. So pike position on the bottom, on the top here we've got the tuck position. And they want us to go through, and it says if the diver gives himself an initial angular momentum of 106 as he jumps off the board, how many turns can he make when jumping off a 10-meter platform in a tuck position? The very first thing we need to do for this one is we've got to figure out the amount of time it takes for him to go from the 10 meters all the way down to the ground. So our time here, in order to find it, we're going to use the equation the change in the height is equal to the original velocity times time plus 1/2 of gravity times time squared. Our time then will be equal to the square root of 2 times the change in y all over gravity, and it's because it doesn't have any original velocity, so that goes away. So to find our time, we're just going to take 2 times 10, and we're going to divide it by 10 and be the square root of 2, which is 1.41 seconds. Now that we know that, let's go ahead and, oops, I don't need an A there, we already have one up here. We want to find out what is the change in the rotation, or what is the change in the angle. That's equal to omega times the change in time. And it's because we know the angular velocity is just the change in position over the change in time. So that's why we can come up with this equation. We also know that L is equal to I omega, so we said angular momentum is equal to I times omega, and so we also can say W is equal to L over I. If we think about how these two things relate, we can now say the change in the angle. I'm going to plug this in for my W here, for my omega. So now I've got L over I times T. We'll plug in our numbers now. This is 108. So here's my 106, not 108, 106 divided by 8. So there's the 8. And we're going to multiply that times 1.41, which is our time. We end up with 18.7 radians per second. Now that we have 18.7 radians per second, let's go through and figure out how many revolutions that is. So we've got 18.7 radians over a second, and we know that in one revolution there are 2 pi radians. So now when I do my math, I'm going to end up with about 3 revolutions, and that's the answer for part A. For part B, we're going to do something similar. We're going to just say that the change in the angle is equal to L over I times T. So that's equal to 106 over, now we've changed, we now have 15.5 on the bottom. So 15.5, and it will take the same amount of time to fall to the ground, which is 1.41. And we want to go ahead and convert this over to revolutions, so we're going to do 1 over 2 pi. So I've just condensed everything we did up here for our bottom problem. This is 1.5 revolutions. We'll only have one more problem to do, and it is super simple. This last one says the distance from the center of a breastbone to the man's hand with the arm outstretched and horizontal to the floor is a meter. The man is holding a 10-kilogram dumbbell oriented vertically in his hand with the arm horizontal. So what is the torque due to the weight about the horizontal axis of the breastbone perpendicular to his chest? So here torque is just equal to the force perpendicular to the radius, and that's equal to mass times gravity times the radius. We know we're holding out a 10-kilogram barbell. We've got 10 meters per second squared, and then we multiply times that 1 meter. So we end up with 100 newtons times meter. I told you that one was pretty easy. And that is the end of the problems that we were not able to do in class.